entropy and Gibbs free energy. Now we've said so far that for a process to be spontaneous or feasible, then the total entropy change, delta S tot, must be positive. Well, Gibbs free energy is a mirror image of that. So for a process to be considered feasible, thermodynamically feasible, delta G must be negative. Okay, and it's a new concept, but you'll get your head around this one. So essentially, delta G must be negative. If delta G is positive, the process is considered to be not feasible, and a reaction that reaches equilibrium, at equilibrium, delta G must be zero. So the overall force is to approach and to attain equilibrium, and at that point, the delta G in the given conditions must be zero. Now let's look at the possible scenarios here. Now this is the new equation that we're going to start working with. Okay, so delta H is the enthalpy change for the reaction, and that can be positive or negative. Delta S here is considered to be delta S of the system. Okay, we're talking about delta S of the system. We've talked about that before. That's exactly the same. So delta S of the system is here, and that can be positive or negative depending on how the level of disorder changes in the process. So let's have a look. If we've got a positive delta H, so the reaction is endothermic, okay, this is positive, and we've got a positive delta S system, so the amount of disorder increases in the process, then if this is positive too, then it's going to be a fight between these two terms, isn't it? Now for the process to be spontaneous, then this term is going to have to be bigger than this term. So delta G will be negative if the magnitude of T delta S is larger than that of the enthalpy change, delta H. Okay? It makes sense then, in that case, that if T is bigger, at higher temperatures, the process is more likely to be feasible. Now with endothermic reactions, and with delta S negative, delta S of the system negative, then if delta S is negative, this term is positive, this term is positive, so delta G will always be positive, so the reaction will never be feasible. If we've got a negative delta H, so this is a negative term, and a positive delta S, so this is a negative term, delta G will always be negative, so the reaction will always be feasible. And then we go back to one of these 50-50s. If we've got a negative delta H, so this term is negative, and we've got a negative delta S, so this term is positive, then it's going to be a fight between the two terms, isn't it? So delta G will be negative if the magnitude of T delta S is smaller than that of delta H. Okay, think about that for a while. We might as well see this because this is a really easy calculation. If that was our equation for delta S tot, if we multiply both sides by minus delta T, we get something that looks like that. We rearrange slightly. We put the delta H here, put this there. Suddenly it starts to look familiar. We call minus T delta S total, we call it delta G. It's now an energy, and delta H minus T delta S is our expression for Gibbs free energy. It's nice and easy. If you forget Gibbs free energy, then you can derive it yourself. So let's look at some examples of this, and let's look at some details of this equation, Gibbs free energy. Remember, for a reaction to be considered spontaneous or thermodynamically feasible, delta G must be negative, and delta S total must be positive. If it's positive, delta G, then the reaction is not feasible process, and if delta G is zero, the reaction will reach equilibrium. But just because delta G is negative, it doesn't mean that a reaction is going to happen, that a process is going to take place. There are three caveats we must consider. The first one is that if the activation energy is high, then the rate of reaction may be very low. So even if the reaction is, the delta G is negative, the reaction is thermodynamically feasible, it might proceed at a very low rate because of a high activation energy. Second consideration is that the reaction may need a kickstart of energy. Okay, so it will proceed. Once it's started, there's no stopping it. But initially, it might need to get off the starting blocks with a kick of energy. And finally, if the conditions are not standard, so you might have a reaction where in standard conditions it looks like it's a feasible reaction, but if you change the 298K or the 1 atmosphere pressure, 100 kilopascals, then, or the concentration of a solution, then you can alter the favored direction of a reaction. And we see this especially, don't we, with reactions that are reversible. We can change the position of equilibrium, so we favor a particular direction. So non-standard conditions is another reason why a reaction may not be spontaneous and feasible at a given temperature. The reaction for magnesium and oxygen, or hydrogen oxygen, are good examples. They illustrate the first 2 points, don't they? They're reactions that will not proceed unless we give them a kickstart. Otherwise, the reaction rate is tremendously slow. Let's have a look at a worked example. Put some numbers into this now. The decomposition of calcium carbonate. Now you know if you've heated calcium carbonate in a Bunsen at room temperature, it won't thermally decompose. But let's have a look at when it does decompose. Okay, so the standard molar entropies for the substances involved are, well, you can look them up. You should get into the habit of searching for these data. So go into Google and pump in the standard molar entropy of calcium carbonate and get a figure. And the same for calcium oxide and carbon dioxide. Standard molar entropy. And there they are. Okay, notice they're in joules per mole per Kelvin. So we can work out the delta S of the system, the change in entropy of the system. And that's the sum of the standard molar entropies of the products minus the reactants. Okay, you can work that out. It's not a difficult calculation. Okay, so the products, calcium oxide and carbon dioxide added together, subtract the reactant, and you get that. Okay, that's the entropy change for the system. This is the expression we're using, so we now have delta S system. At 25 degrees C or 298K, we can work out delta G now, because we've got the information. We've got the enthalpy change, careful, kilojoules, and we've got the temperature, 298. So we plug those numbers in, we get that. Okay, it's positive. What does that mean? It means that at 298K, calcium carbonate will not thermally decompose spontaneously. The reaction is not feasible. Okay, so we could have a graph here. This is quite an interesting graph. If we look for 298K on this scale, look, this is a temperature scale, so 298 is going to be down here somewhere, isn't it? Delta G was very positive, so it's not spontaneous. But as we increase the temperature, then this reaction at some point becomes spontaneous. It's not standard conditions anymore, and at some point it becomes spontaneous. Okay, so we could ask ourselves the question, what is the temperature? How can we work it out? At what point does it become thermodynamically unstable, and the reaction or the decomposition becomes spontaneous and feasible. Okay, let's calculate this. So delta G is that, and what we do is we assign delta G 0. We're looking for when the reaction becomes spontaneous. So if we make this 0 and plug the numbers in again, obviously we're working out T, do some rearranging, and you get T is 1079 K, which is around where it shows on a graph. Okay, so above that temperature, the thermal decomposition of calcium carbonate is feasible, spontaneous. Right, read the pages and answer the questions therein.